let's take a look at section 2.5 and 2.6. 2.5 is on series resistors and voltage division, and 2.6 is parallel resistors and current division. So parallel and series we've looked at before. The techniques in these two sections are a way to combine resistors to make the circuit smaller and a little bit easier to deal with when you're solving for things like voltage and current. So if we have a simple circuit here with two resistors, R2, R1, and we'll say just some V, let's call S for source, V1 and V2. So we can quickly find the voltage of V2 by saying that V2 is equal to this resistor R2 over R1 plus R2 times the source Vs. Now the reason we can do that is because of Ohm's law, and there's a proof of that in the book. I'm not going to do that proof because you can read a book. So go ahead and pause this video, look at that section if you haven't already read it. You should be reading the sections before you watch the videos. But for voltage division, it's very simple. It's the resistor that's connected to the voltage that we want to know about divided by the sum of the other ones. So if I want V1, then my R1 goes on top. R1 over R1 plus R2 times my source Vs. So as the book states, this is for resistors in series. Okay, that's very important. One other thing that they also talk about in this section is how to combine resistors in series. You just simply add them. So if I have any number of resistors in series with each other, then an equivalent resistance, so I could replace all those resistors with one equivalent, Req, that is simply the sum of these resistors. Again, this is for series resistors, and they must all be in series. So if I have a resistor coming up this way, they're no longer all in series, right? R1 and R2 would be in series, and R3 and R4, but not R2 and R3. They all have to be in series. So this is voltage division. And series. Voltage division is very, very useful, particularly in electronics. So those of you that will take the electronics series really want to get a good grasp on voltage division. We will use it over and over and over and over again, as well as the combining of resistors. That's a very important concept to understand. So section 2.6 is current division and parallel resistors. So again, the proof of this is in your book. Let's take a look at this. So elements in series have the same current, right? This current flows all the way around here. Elements in parallel, these three are in parallel, they share the same two nodes, all have the same voltage. So my voltage Vs, remember what voltage is? The potential difference between 2 points. So the potential difference between here and here is the same as the potential difference between here and here, because it's the same node. Again, sharing the same two nodes, Vs. So that voltage stays the same across all of these elements in parallel. If this is R1, and we have some current I1, and an I2, and an R2, we can use what's called current division. Again, I expect that you're reading your chapter. Current division, if I want I1, then it's going to be the opposite resistor, R2, over the sum, R1 plus R2, times my source, which I think the book actually, when they teach this, they do it as a current source I. So let's go ahead and do that as well. So let's change this. Well, we don't have to do that. We can just draw in our current source IS. This will be times current source IS. That's fine. That's saying the same thing, right? So our source current is right here. We could draw that as a current here. We could draw that as a current here. That's current division. So if I want I2, again, opposite resistor, R1, over R1 plus R2 times my source current, IS. So that's current division. We can combine resistors in parallel by doing the reciprocal of the sum of the reciprocals. I know that sounds confusing, but let's take a look at it. So if I have resistors in parallel, again, this could be as many as we want. I'm just going to draw 4. R1, R2, R3, R4. And I want to know what my equivalent resistance is. I want to replace all those with one resistor. Then my REQ is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4, however many we have, to the minus 1. And again, the proof of why this works is in your book. We're not going to do that here, but this is for resistors in parallel. Now, a little trick if you only have 2. So if we only have 2 resistors in parallel, because of algebra, I can do R1 times R2 over R1 plus R2. That is the same thing. But again, that's because of algebra. So don't make the mistake of saying R1, R2, R3, R4 divided by R1 plus R2 plus R3. That does not work, okay? You can only do this shortcut when you have 2 resistors in parallel. And that is often the case. So it's a nice little shortcut to remember, but you have to keep in mind that it's only for 2 resistors. You have more than 2, you need to do it this way, with all of them 1 over itself, and then to the minus 1. You can watch the next video for some example problems.